Yeah, welcome back to our course on energy transition. We last time talked about units, the idea behind energy transition, and the different sectors and tasks to do. The conventional energy supply will be discussed today. So we'll talk about conventional power supply, just as coal, gas, oil, nuclear, some simple thermodynamics, capacity factor, composition of energy systems, grid levels, composition, and daily and seasonal load. The rest then will come to solar irradiance. So we have then the use of first fluctuating renewable energies, and then we come to not fluctuating renewable energies, and then we come to storage technology, and then the combination of all, and perspective and feasibility of energy transition. We'll discuss some simulation tools, and finally we'll do an excursion. So for today we have basics of conventional power generation. So you see here the basic outline is we have primary energy. We convert that into kinetic energy or heat, and then we convert that into a rotation energy, and then we convert that rotation energy into a secondary energy, mostly electrical energy. Let's take the first example. So we have here a water reservoir. We put them through a pressure type, then on a water turbine. Then we have rotation energy, and we convert that rotation energy into electricity via a generator. A nuclear power plant, we have a steam generator via kind of combustion chamber. If you compare it to power plants just as coal or lignite or gas, and then we have steam, and we use the steam turbine to generate rotation energy, which we will put into the electrical generator, and as a final energy we have electrical energy. As I mentioned already, for fossil fuels, whether it's gas, coal, or lignite, it's about the same. So we convert it into heat energy. We use a gas turbine, and then drive a generator which converts that into electrical energy. We can also use fossil fuels such as diesel or gasoline to drive a combustion engine which drives a generator. The upper line is just the same as before, just is a basic principle. If we then on the second line use a solar collector, we can heat up water or any other media, create steam. This steam goes to a steam turbine, and we have a generator of electrical energy. Another possibility is using wind power. So we don't need any intermediates. We can directly use wind energy to convert it into rotation energy, which drives a generator, and convert that into electrical energy. We can also have even more direct conversion if we convert sunlight directly into electricity via the photovoltaic principle, via a solar cell. Also, we can use hydrogen to convert it into electrical energy via a fuel cell. To give you some ideas about the conversion efficiencies, so if we have a modern hydropower plant, efficiency above 80%, sometimes over 90%, really bad ones are 60 or 70%. A coal power plant, on the other hand, is quite limited in efficiency due to the Carnot efficiency, which says that the maximum efficiency is dependent on the temperature difference you can achieve there, and due to the materials this is also quite limited. So even modern coal power plants have an efficiency in the vicinity of 40-45% if you can't make use of the heat If you just consider the electrical conversion efficiency, this is quite limited. Wind power plant, it's about 40%, a little bit more for most modern power plants. Nuclear power plant, also relatively low, with 33% of conversion efficiency. Mostly you don't make use of the heat. Just to give you an idea, a dynamo, this is a synchronous generator, a bicycle, 20 to 60% of conversion efficiency. Solar cell, really bad solar cells, they are below 10%. Most solar cells on the market are in the vicinity of 18-20% of conversion efficiency. The best lab cells are in the vicinity of 29. There are even some lab cells which are close to 40%. Here we see the scheme of conventional energy generation. So we have fossil fuels which come into a combustion chamber. We use oxygen to oxidate them. Then we have polluants, carbon dioxide, and wastewater, which will be depleted into the environment. If we have a sustainable use of energy, we'll use renewable resources of energy, and we generate electricity without that heavy impact of the environment. So we think in a cycle and take a look at what's left over, and here if we think in a sustainable way, there is not much left. Here is a general so-called Sankey diagram. So this the thickness of the arrows shows the amount of losses what we have here, or the amount of power flows or energy flows. So first we have a primary energy. If you think of fossil fuels, most of the energy at the first conversion will be lost due to heat. So as I mentioned, nuclear power plants is about 67% that will be lost. At the conventional coal power plants, it's about 60% that will be lost. So we have our secondary energy, and then if it's in the electrical level, the losses are relatively small. Transformers are quite efficient. Power lines are also quite efficient, and also the machinery, electrical engines, are also quite efficient. So the losses are relatively small, as you see by the size of the light blue arrows. So I mentioned here the maximum conversion efficiency at thermodynamic machines is given by the so-called Carnot efficiency. So that is 1 minus the minimum temperature divided by the maximum temperature. The higher the difference between minimum and maximum is, the closer it is to 0. So if you have really high temperature, then the Tmin divided by Tmax is really small, and then the conversion efficiency is very close to 1. But usually this is quite limited, so therefore the conversion efficiency of thermal power plants are quite low. Here you see the energy flow again of a fossil fuel power plant. So of the more in detail now, you have the chemical energy coming in, the burner. Then you have some losses already there, as indicated by the yellow arrow that goes down. And then you have the remaining heat energy which goes to the boiler, and this is then converted into steam. This goes into a turbine, and this kinetic energy goes into a generator, and then you have your desired electrical energy. All these steps are related to some losses depending on the layout of the whole system. To have a high efficiency in terms of the Carnot efficiency, it's important that you have a high temperature difference between minimum and maximum temperature, so you cool down the exhaust of the steam turbine in order to achieve a low temperature. Then you need a pump in order to get the high pressure here, and so on. We discuss this a little bit later in detail. Nuclear power plant, as I mentioned before, is quite similar. instead of a combustion process, you have a nuclear chain reaction which emits heat, and you use that heat to power a steam turbine and then generate electricity. Also, to have a high efficiency, you cool down the exhaust. Theoretically, you can make use of that heat, but nobody. It's a bit also a safety issue whether you want to get your heat from a nuclear power plant. Germany, that's not used. Some countries, I think Korea, they have really a connection to the power plant to heat their houses. This is a side of a coal power plant here. First, some thermodynamic basics here. So we talk here about the specific heat, so-called heat capacity first. So if you want to heat up water, how much energy you would need to a certain temperature. And so you have here the amount of heat by a big Q. And then you have the C, the specific capacity. And then you have the delta T, the temperature difference, and the mass. For example, 1 liter of water will be equivalent to 1 kilogram. So the specific heat of air is quite low. It's about 1 joule per gram Kelvin. If you have water, it's 4.18 joule per gram Kelvin. Just in other words, you need 4.18 joule to heat up 1 gram of water by 1 Kelvin. Then quite interesting to see is a phase change. So you have then the absorption or emission of heat without any temperature change due to the phase change of a material. And for example, from ice to water, you can put lots of heat in without a big change in temperature. This takes place at a constant temperature at 0 degrees, and that is 334 joule per gram. So it's quite a lot. If you compare it to the 4.18 joule per gram Kelvin that you have for heating it up, this is equivalent to quite a big temperature difference. We take an example. So we take 1 liter of water that is equivalent to a mass of 1 kilogram. How much energy we need to heat it up? So it's 334 joule per gram times 1000 grams. That's 334 kilojoule. You need to do that. If you go further, if you're close to, at 100 degrees Celsius and you want to evaporate boiling water, you need QV, the required heat to evaporate it, and that's even higher. That is 2258 joule per gram. And for example, if you want to evaporate that 1 kilogram of water, you need 2.258 megajoule to do that. It's about 8 times more than the latent heat into from ice into a liquid state. Here are some properties of different materials. For example, here first is alcohol. So it has a boiling point of of 78 degrees, a freezing point of minus 130 degrees, and so on. So you have all the different materials. You see water here, and the second line is just as a second, how you call it? The second part here is the phase change from liquid into vapor, and the first is from the solid state into the liquid state. And here the L is the equivalent energy needed to do that in a kilojoule per kilogram. It's the same as gram per joule per gram. Also quite important is the calorific value or heating value. That's the total energy released as heat when a substance undergoes complete combustion with oxygen under standard conditions. The chemical reaction is typically a hydrocarbon or any other organic molecule reacting with oxygen to form carbon dioxide and water. Release it may expressed into with quantities in energy per mole of fuel, so joule per mole, or energy per mass, so this is joule per gram, or energy per volume. For example, if you have gases, joule per cubic meter. The quantity known as the higher heating value, HHV, or gross energy, or upper heating value, or gross calorific value, GCV, is determined by the internal chemical energy being theoretically available for combustion, but often there is the material is wet. It contains some water which has to be evaporated, but which cannot be used directly for the combustion process, and therefore for us it's more important the so-called lower heating value. So that's the net calorific value, and we subtract the energy needed for the evaporation of the water that is contained in the material. For example, at wood or even at coal, you have some water contents there. So to give you some values, so the lower heating value for natural gas is about 50 kilojoule per gram of coal. This depends on the quality of coal and so on. This is in the vicinity of 25 to 33 kilojoule per gram. Diesel 43.4 kilojoule per gram. Hydrogen has the most, 120 kilojoule per gram. We talk about not only about energy values, we have also to think about carbon dioxide emissions. And if we only think about first about heat generation, not electricity yet, we have to multiply then with the conversion efficiency of the power plant. So the specific carbon dioxide emissions will be significantly higher. For example, at a conventional power plant, almost factor of 3. Just is for heat production now. So natural gas, we have an emission of about 56.1 kilogram of carbon dioxide per gigajoule of heat release. Or if we substitute the gigajoule by kilowatt hours, it's equivalent to 200 grams of carbon dioxide per kilowatt hour. For coal, it's significantly higher. 94.9 kilograms carbon dioxide per gigajoule. Lignite even more higher, 104 kilogram carbon dioxide per gigajoule. Diesel is a bit lower, same as gasoline. Hydrogen, sure, there is no carbon dioxide emission. It's just emitting water vapor at the end. If we think about electricity generation, as I mentioned already, we have to multiply that carbon dioxide emissions by a factor of about 3. So we have here the combined electricity and heat generation. This increases the total efficiency, while the problem is we have to have a consumer of heat. That's no problem. Winter, many houses need heating, but in summer that's a problem. Many houses don't need heating anymore, and what to do with the waste heat. So this is sure the turbine and the electricity is always needed, but with the heat possibly you only have a consumer during the winter period. Here you see gas and steam combined power plant, so you can increase the conversion efficiency significantly by combining a gas turbine with a steam turbine. So efficiency can go up from 38% maximum, maximum up to 55 to 60%. This is a gas turbine here made in Berlin-Moabit by company Siemens. You see the different stages and the different compression levels of the wheels here. Also, you can combine that gas and steam turbine also with district heating. So if you have a consumer for heat, that's very helpful, so you can achieve a very high efficiency, so that if you add to the electrical efficiency, then the thermal efficiency. There's only very few opportunities where you can add efficiency. Usually you multiply efficiency, but here, while you have one electrical efficiency and the other one is thermal gain, you have the thermal efficiency and you can add them. So these are some examples of final energy use in Germany. So from you see that a lot, or most is needed as mechanical use of energy. That's basically traffic, cars, and so on. They run on mineral oil. The efficiency is not very good. Conventional combustion engine only has an efficiency of about 30%. So 70% is converted into heat and wasted. The next is space heating, almost 30%, 28%, which is required to that. And the other processes, heat and so on, this is just IT. This is don't account so much, but we come to details a little bit later. This is a primary energy consumption. The sectors should update this. I present you later some newer data on that. So as before, the main primary energy consumption is mineral oil, because the very most 99% of the car run on mineral oil, and therefore it's needed quite a lot. Then it's a natural gas, hard coal, lignite, and the renewable energy sources are relatively small. This is sometimes due to the way how this primary energy consumption is calculated, because usually you would think about if you have 1 kilowatt hour of electricity, you can either generate it via coal or via renewables. And if you generate so you would need about 3 times the calorific values of coal than you would have if you use the same amount of wind power or solar power. And but not the way how they calculate it. They calculate that with the so-called efficiency method. So they say that the output of the renewable power plants, the electricity is accounted for as primary energy, and therefore the share of renewable energy shares is relatively low. That's a global overview here where energy is consumed in the transportation sector. So here you see most is used for cars and motorbikes. Then you have here a road and flight transport, and so it's just a quick overview on that. The development of Germany in renewable energy is quite good. Not good enough for really coming to a significant reduction in CO2. There is reduction, but not very much. Most reduction takes place in the electricity sector. Unfortunately, the mobility sector, because people are buying more and more heavy cars, the carbon dioxide emissions is rising there. But due to the increasing use of renewables in the electricity sector, the total carbon dioxide emissions are going down at least a little bit. Here you see different sources here. The yellow one is photovoltaics, the blue one is wind power, the green one is biomass, The red one is geothermal power, not very much in Germany. They don't have a lot of potential for it. And the dark blue one is traditional water power, as you see from the numbers 1919. There basically was only water power as renewable energy. So renewable energy in the heating sector, see that has been increasing for a while, but now not very much. We're a bit stagnating there. And transportation sector, same issue. This was basically caused by biofuels, but later they found out that these biofuels have not been sustainable. So they found out that some Indonesian rainforests have been cut down to plant to get palm oil in order to substitute mineral oil and so on, and so it even decreased a little bit the use of that biofuels. As a renewable energy share is increasing, the latest number now from 2020 to now is that we have 55% of renewable energy, of renewable electricity in Germany this year in 2020. The number of terawatt hours here generated energy. So we have the wind energy sector, which is also increased quite a lot. Also photovoltaics stagnated after the year 2013 a little bit due to some limitations. There was a limitation of 52 gigawatt, which everyone was afraid of, including the investors, and so they haven't been done so much last years. The latest development is that this 52 gigawatt limit is lifted, and so there is a possibility to install more photovoltaic power plants with advantages that you have priority for grid injection and get a fixed injection tariff for 20 years, which is quite helpful to make a business plan for photovoltaic power plants. Biomass, as I told you, is increasing, but not as much. Hydroelectric, yes, a quite good source, but unfortunately, due to the geography of Germany, we have relatively a small amount of mountains. It's limited to 3 to 4% of the total electricity consumption, but there can be done a lot for its conjunction with neighboring countries such as Switzerland or Austria, or what has been already carried out by the Netherlands, make a power line to Norway. There is enormous potential there. They have only a single lake system, Lake Blase, which has a potential of about 7 terawatt hours of storage capacity. So it's about almost 1,000 times more than the Goldestal storage capacity. Germany is building a power line also to Norway with a maximum power of 1.4 gigawatt. It should be finished this year, but the capacity is relatively small. If you really think about balancing out the fluctuating wind and solar power generation, think about 10 or 20 times as big this power plant in order to have a significant effect on the energy balancing in Germany. Energy from waste sector, okay, it increased, but in general, that's not a very high level. And these are the according avoided greenhouse effects, greenhouse gas effects. I give you also a newer representation on that. Let's come to the grid. How is a conventional grid being set up? So you have first the interconnection between the power plants. This is so-called transmission grids. It occurs on a high voltage level between 220 or 380 volts, kilovolts. Nowadays, people say that the 220 kilovolts gets eliminated and we only will have 380 kilovolts. And here the large power plants are interconnected, even countries are connected inside Europe at this voltage level. Then we have a medium high voltage level, which is about 110 kilovolt. So this is for big industry and research centers and so on, and it's not directly used for rail transportation, which only works with 15 kilovolt and a different frequency. but transformers are fed with that voltage. Then we come to medium voltage. For example, our university is connected to the medium voltage grid, which is nominally 20 kilovolt, but there are some smaller cities and so on which have different voltage, for example 8 or 6 kilovolts, 10 kilovolts and so on. And then we have the low voltage grid with a three-phase system. It's 400 volt between two phases. If you take the voltage between phase and neutral, it's 230 volts, 60 hertz. This is different in some countries. So some countries have lower voltage, like Japan. They have only 100 volts. Frequency is all the same in whole Europe and Asia, including Africa. Only the Americas, they have 60 hertz. And the north part of Japan, it's quite interesting. The north part of Japan has 60 hertz, and the south part of Japan has 50 hertz. Same a bit in some countries in the American continent. Paraguay, for example, they have a 50 hertz grid, while Brazil or Argentina, they have a 60 hertz grid. And United States and Canada also has 60 hertz. Okay, you see here conversion like is formerly. Nowadays is all less visible, but this was traditionally in the 60s and 70s. You saw such transformer stations from with mid voltage for a small village to 400 volts, and this 400 volts is then delivered to every household in 3 phases and then split up. For example, single phase use to have 230 volts. Here you see the distribution grid. Here nowadays in Germany, most is underground. We have here the load curves, what you see here. So traditionally we have some base load. That means power plants that are working 24 hours a day and or even 365 days a year. And these are lignite power plants. They have been set up and built and designed in the 60s and 70s. So they are not flexible at all. They are just made for making cheap electricity at a constant level. Then we have medium load. There you need more flexibility. Traditionally, this has been the hard coal power plants in Germany. So they are a bit able to cope with that. So they can be throttled down or speed up a little bit. And then a peak load, which was traditionally made by some hydropower plants or gas power plants. They can be throttled down or speed up within a couple of minutes. As I mentioned already, the hydropower plants can do it within 1 minute, and the gas power plants, they need about 5 to 8 minutes to do that. On the left part, we see a typical summer day. On the right part, it's a typical winter day. To make maximum profit with their baseload power plants, the consumption structure has been altered. So first you see the consumption during a day in the 60s. So people were sleeping, they didn't consume a lot of energy during nighttime, and they were working during daytime, so consumption was significantly higher. That's a light green curve, what you see here. That is this curve here. And while the electricity companies wanted to use more baseload power plants, they gave special tariffs for consumption at night. So a lot of houses, they even do heating by electricity, and they gave in the nighttime, they get very cheap electricity prices. And therefore this pattern has been altered, so the consumption during nighttime increased significantly. Okay, lifetime changed also much, but basically this was due to the better use of the baseload power plants and the special tariff for that. So you see here the available power at maximum load. So this also traditionally, so you say there's a maximum load, and they call, usually the traditional people, they call not applicable power. That means wind and solar power, because they don't know whether this power is available and so on. And that's a bit of pity. So they always want to make sure that all power needs are satisfied, and therefore they need the full power in Germany as conventional power plants as a backup, which is not true. We have some certain base, even if you have no wind or no sunshine, there is still production of renewable energies, and this could be added to that. But in general, we can say the maximum load what occurs is usually during winter time, around Christmas. I think that the third Wednesday before Christmas, this is usually the highest load in Germany, which is 76.7 gigawatt of load. So a reserve of about 6 gigawatt. This is a German high voltage grid in 2006. They want to improve it a little bit, because there's a lot of wind power in the north part of Germany, but the industry is more in the middle and southern part of Germany. So there, since almost 10 years, there's a construction of new power lines there to transport the high amount of wind energy from the coast or from offshore power plants to the south. Not only inside Germany, there's a whole interconnection over Europe. So this can be really helpful if you think large scale. You can also profit from the different time zones. For example, Portugal is a time difference of about 2 hours to Germany, or even 3 hours if you consider Russia and so on. And that means this time difference also applies for the availability of sunshine, and you can make use of that. Also, there's a different availability and probability of wind power at the different region, and the European grid can be used to balance that out. To see these numbers and lines also this is in terawatt hours, what is happening during 1 year in interchange. The grid types. So we have here traditionally the radial grid. This has been also when at the introduction of electricity in Germany, it has been also like this. Many countries, just as the United States, they still have the radial grid. It's the cheapest way to make it, and it's quite simple. So you just have like a star, you have just a power plant, and then you have the rays which go out and to the different consumer. The problem is if a failure occurs, you have a lot of people without electricity. There is no backup. A bit better is the ring grid. So even if a failure occurs, you can isolate that failure by switching off that part. For example, there's a short circuit here, so you can switch off that part. So these people will be without electricity, but all the rest will still be supplied by electricity. Can even have a more meshed grid and then you have a very small areas or regions which don't have electricity in case of a failure. And this is more costly, but in general it's a more reliable grid. This also being shown here with the so-called SADI value. This is a system average interruption duration index. So the higher this index is, the more failures occur. And you see the development here in Germany that's really going down, because some people say, this renewable energies or this energy transition makes the grid more unstable and so on. As these numbers confirm, the opposite is true. So in 2006, we had an SADI value for total SADI value of 21.43, and in 2015 it was about half of that only. So the duration of power failures was reduced by 50%. You see that we are quite good here in Germany there are many other countries which have a much higher blackout times. And opposite to what many people say, it's not related to the use of renewable energies. So what you see here is the energy flow chart of Germany, not only electricity, that counts for all types of energy. You see that most of the energy is imported, is in the left part, the import. This is 13,431 petajoule. So this is a joule with 10 to a power of 15. But some considerable amount is also by own production. Here about 3,000, how much is it? 886 petajoule. And then there's some stock which gets removed. So we have a total primary energy supply of 17,486 petajoule. And yes, with primary energy, as I already mentioned, we don't have to consider all primary energy, present energy supply, if we do an energy transition, because some of the processes are rather inefficient. So a lot of energy is wasted due to heat production. For example, if you do room heating and you would use a heat pump instead of burning fuels, then it would be more efficient. Also, if you would have an electric car instead of a combustion car, this would also increase the energy use by a factor of 3. And then we have some part which goes into export. Maybe we can amplify this a little bit. Yes, here see it better. So some of the primary energy part is exported or goes into marine bunkering. And so we have as leftover the so-called primary energy consumption of 13,106 petajoule. Some statistical difference, but also we have non-energy consumption. For example, if you fabricating plastics and so on, this is accounted here. And then you have transformation losses in the energy sector. This is quite considerable, as I already mentioned. And then you have own consumption in the energy sector. There's also some differences if you see some different table. For example, if you have tools to evacuate or to mine coal and so on, this also consume energy. And in my statistic, I'm always using the net consumption, not the gross consumption, but it's always used because we are more interested in the energy that arrives at the consumer. In some statistic, you find this consumption in the energy sector included in the consumption. The end, we have, not at the end, but then we have the so-called final energy consumption amounting 8,996 petajoule. There is almost equal share going to the industry of 2,651 petajoule. For transportation is used 2,705 petajoule. Households are using up 2,291 petajoule. And trade, commerce and services a little bit less. It's 1,350 petajoule. Now we come not only to energy, but to electricity. This is a year later in 2019, and the split up of the different types of power plants included. So we have here on the left side, you see all kinds of power plants, including renewables and non-renewables. You see that wind power is taking a large part, then followed by lignite, and brown coal. Nuclear is also still on the way, then it's photovoltaics and biomass. In total, we had in 2019 46% of renewables share. So that's quite a lot. Nobody expected it 2 decades ago. So during these periods in 2000, we just started with 3% of hydropower and wind and solar were practically non-existent. If you go a step further, see what's happening in 2020. So this data have been captured until the 2nd of July 2020. You see it even increased. It was probably due to the corona crisis. There was less energy consumption, so the fossil fuel power plants have been throttled down a bit. Plus there was quite a lot of wind power during the first month of 2020, and also a lot of sunshine during the first half year of 2020. So in total, we had there 55.7% of share of renewables. So more than half of the energy this year until now came from renewables. If you take a world perspective and take a look at what kind of power plants are installed worldwide, you see that in 2019, most of new power plants that have been installed were solar, with a new amount of installation of 117 gigawatt. Nominal power, that's not the energy being generated. We come to this later. We have to include the full load hours or the capacity factor. Then followed by wind, 61 gigawatt, then gas, 30 gigawatt, coal, 18 gigawatts only, hydro, 15 gigawatts, other renewables, 5 gigawatt. Some people are asking, why is there nuclear? There in 2019, there has been a higher nuclear capacity dismantled than installed new, so the net was below zero. So therefore, there are effectively no nuclear power plants during 2019. Let's come to the full load hours. That describes that the actual generation, energy generation during a year, divided by the installed nominal power capacity. So if you are running at full power all the time, then you have to consider the amount of hours during a year. That's 24 times 365, 8,760 full load hours. If you can also consider the so-called capacity factor, or CF, that's a ratio of an actual energy output over an amount of time, which is usually a year. Could also be over lifetime, for example 20 years or 40 years, to the maximum possible energy output over the same amount of time, for example also a year. So if you have a capacity factor of 1, that means your energy generator is generating all year round the nominal power, is generating with the nominal power during the whole year. This is now a part of your homework. You got some statistics from renewable energies in Germany. This includes hydropower on the bottom right, it includes photovoltaic on the bottom left, it includes wind power on the right. So on all of these graphs you have the installed capacity. On the last part is 2015. And you have the total installed capacity until that date, and the generated energy during electrical energy generated during that year. And you have to calculate the capacity factor for the different sources of energy. You find out they are quite different. For example, if you have hydropower, this is the use is quite good. Wind power, also still quite good. Photovoltaics, there are better places than Germany to install photovoltaics. So this will be in the vicinity of 10%. And if you go to biomass, this is utilized quite good. So the capacity factor will be in the vicinity of, don't remember, it was about 30% or so, or 50%. That's your homework to find out. Yes, and we have also a second exercise as homework for you. First, I just do a repetition so you can carry it out on your own. So we discussed about the required heat if you want to melt water, so from ice to water, both at 0 degrees, you will require 334 joule per gram. And for example, if you want to melt 1 kilogram of ice, you have this formula Q as L times LF, that's for fusion, L times M, and this is 334 10 with multiplied 10 to a power of 3, because this is kilogram, joule per kilogram, and you have 1 kilogram, and then you have 334 kilojoule, what you need for that. Then further, if you have boiling water with 100 degrees and you want to convert it into steam at the same temperature, you need specifically 2260 joule per gram of water. So if you want to evaporate 1 kilogram of water into steam, you need 2.26 megajoule. So now your exercise is how much energy you need to heat 1 liter of water from 14 degrees, that is usually the groundwater temperature, to the boiling point at sea level. If you want to vaporize 1 liter of water from the boiling point at sea level. And third is to melt 1 kilogram of ice. And then is asked how much fuel you need to do that. So we take natural gas as an example and hydrogen. And the question is how much natural gas in grams and how much hydrogen you need to do the upper tasks here. And you have to consider an efficiency for the heating processes of 0.9. Additional data there. There is a specific heat of water, which is C is equal to 4.18 joule per gram Kelvin. The latent heat of water for fusion is, as already mentioned before, 334 joule per gram. For evaporation, it's 2260 joule per gram. The low heating value for natural gas is 50 kilojoule per gram. For hydrogen is 120 kilojoules per gram. That's it for today. Thank you very much for listening.